Guys, this is going to be unit 8A.5. This is going to be called Zeros of Polynomial Functions, and it's divided into two parts. I just want to review some vocab before I go ahead and go into any of the problems. A zero, this was from last unit, is also known as a root. It's known as an x-intercept, and it's also known as solution. I also want to recall the vocab of the rational number, which is any number that can be written as a ratio of two integers. In other words, like 3/4, and I'll talk about that in a little bit. Let's go and find all the zeros of this function, and please go and pause the video here. This is review. Try to solve that problem on your own, and I hope that this is what you got. I want to point out that from now on, any polynomial that we're going to be looking at, please check first, is it factorable? Because throughout this section and the next section, we're going to be looking at techniques to factor polynomials that you may not have seen before. And you always want to check first, is the polynomial that you have factorable just by looking at it? This one is, and it's factorable by grouping. I took an x squared out of the first two terms, and then I also took a positive 9, out of the second two terms. And that's how I got a positive 9 there with an x plus 3. And that's how I got an x squared with an x plus 3. And undoing that factoring, so putting this into factored form, I get x squared plus 9x plus 3. I said both of those factors equal 0, which is the zero product property. And when I solve for these, I got x equals plus and minus 3i and x equals negative 3. And I hope that this was just review. Let's go and keep going. So I wanted to just review what rational numbers are and irrational numbers because we're going to be talking about those a little bit more. Rational numbers could be something like 3/4, 1/5, negative 5 could be a rational number, 0, negative 5. Any numbers that are kind of clear, they don't always have to end, but it's a number that is going to can be written as a ratio of two numbers, and both those numbers have to be integers. That's the mathematical definition of a rational number. An irrational number, we've seen before, and an example of an irrational number, the most famous one probably, is going to be like pi or the square root of 2. We'll learn about another irrational number called e a little bit later on. And then ones that aren't so popular but still classify as an irrational number are like 0.01, 0.02, 0.3. And if I keep that pattern going, that number is also going to be an irrational number. And you might be thinking, well, there's a pattern, and irrational and rational numbers usually have patterns as well. The difference is for an irrational number to actually be defined as such, is the number cannot be written as a ratio of two integers. Numbers and irrational numbers throughout this section and throughout the rest of the unit. So it is worthy to review the vocabulary and make sure you understand it on your own. Here's why it's going to be important. We're going to talk about the rational zero test. And it says the rational zero test is a polynomial with integer coefficients, which is what we have here. These are all integers. And if p over q is a zero of p over x, whatever that means, then p is a factor of the constant term and q is a factor of the leading coefficient of p of x. The factor of the constant term. Constant term is going to be 12. This is going to be the value of p. Factor of a leading coefficient. The leading coefficient is 5. That's going to be q. Now, it says the words factor twice. Factor, factor. So here's what we're going to do. We're going to go in and list out the factors of 12 first because it started with p first for some reason. So we'll start off with the factors of 12. And the factors of 12 are 1 and 12, 2 and 6, and 3 and 4. I'm going to repeat the same things for q over here. The factors of q of the number 5 will just be 1 and 5. So what the rational zero test is saying is that p over q is a zero of the polynomial, which means that if I take the p and I take my q and I divide them, I will actually be able to get possible rational zeros. Mr. Lakin, what are you talking about? Bear with me here for a second. It's actually a lot easier than I'm making it right now. First of all, I want to please note 1 is a factor of positive 12, and so is a negative 1 if 12 is negative. All of these numbers will be plus and minuses for factors of 12. Similarly, for 5. And what I do is I take p over q. So I take all these factors of p. Oh my goodness, this is too much, Mr. Lakin. And I divide all these factors by q. Then what I get is a lot of numbers. Let's go and see what we get. We get plus and minus 1. If I take 1 divided by 1, a positive or a negative, I get plus or minus 1. I also get plus and minus 1 over 5. And I can't really break up this 1 in the numerator to any of the other numbers, so that's kind of where I end. I also get plus and minus 12, and this isn't going to be organized numerically. I'm just listing out a whole bunch of combinations. I also get plus and minus 12 over 5. I get plus and minus 2 when I divide 2 divided by 1, and I get plus and minus 2 over 5. I hope you see the pattern now, so I'll just list out the rest without actually talking about it because you're probably tired of hearing me talk, and I'm talking right now anyway. And, oops, forgot one. And now what we have is we answer the question. This is the list of all the possible rational zeros that the polynomial could have. Is the polynomial going to have all of these rational zeros? How many of them are there? 1, 2, 3, 4, 5, 6. That's 12, but it's a positive and negative, so there's 24 possible numbers. Will our polynomial have 24 possible x-intercepts? And the answer to that is a no. It's a resounding no. And what we're going to need to use is synthetic division and a graphing calculator to actually see how this process actually works. Please bear with me. But the answer to this example is in purple. So let's talk about why we care for a second. I had all these numbers. I'll be honest with you, we don't really care. Because we have graphing calculators that are pretty powerful, we can actually find the zeros, rational or irrational, by the calculator by using that zero menu, which I hope many of you, if not all of you, have used before on your calculator. But let's say you don't have a graphing calculator. The reason we care is we can find rational zeros without looking at the graph. Now, which do you think is cooler? That, finding rational zeros without looking at a graph, or cat memes? That's right. That's right. You know which one's cooler. So here, we're going to find all the zeros of this function. The first thing that I'm going to do this is I'm going to graph 5x to the fourth, this function, into my calculator. And I have it right here. Now, once I enter that equation, I'm going to go in and graph that, which gives me this function. Notice where my zeros are on the graph. On the graph, it looks like it's about -1, and it also looks like it's about, I don't know, -1.5 something. So let me go back here. It looks like my roots could be at -1, and it looks like it could be at negative 5. I'm sorry, negative 1.5. It also looks on the other side like I have like a 1.2 and a 1.4, but I'm totally making these up. I have no idea what the actual value is. I'm just guesstimating here. But here's the idea though. If I go back to this page here with the rational zero test, the idea is that I can actually narrow down which possibilities from this purple box will actually be on the graph. And I said that negative 1 and negative 1.5 look like it could possibly be a 0. So if I take a look back at this box, that means that a lot of these options are not going to actually be a 0 of the function. So here's what I'm going to have you do. I gave you kind of a starting point. Please pause the video now and then see if you can find all the zeros. There's 4 of them. Find all zeros of this polynomial, please. They can either be real numbers or they could be complex numbers. Pause the video now. So hopefully you were able to find some of the zeros there for this polynomial. Let me go ahead and go to this page with the answer. I listed out all the zeros here. And I said before at the beginning that it looked like positive 1, it looked like negative 1 and negative 1.5, and it looked like 1.2 and 1.3 were possible zeros. What I listed out this list here for is to show you that a lot of these numbers couldn't qualify then. Like plus or minus 12 is not a possible zero because it's the possible zeros that I saw were these 4 numbers. Positive and negative 12 are too large, which means 6 was out, 4 was out, 3 was out, and 2 was out. There are also some other numbers that we could take away here from this list. Some other numbers that we could take away, again, it looks like all my numbers have to be bigger than 1 in a positive and negative direction, which means that numbers that are smaller than 1 don't qualify. So 4 over 5 is probably out, 3 over 5 is out, 2 over 5 is out, and 1 over 5 is out. So all that remains is a plus and minus 1, a plus and minus 6 over 5, and 12 over 5 is actually 2.4. That's too big, so that's out. I want to back up for a second here. I gave you these numbers before, and I want to make sure again that I'm kind of hitting home exactly what it means. The reason I gave you these numbers is that one of these numbers possibly could be on the x-axis for this graph when we graphed it. That by looking at the actual graph of the function. So the whole point of doing the P over Q thing is if you don't have a graph, or even if you have a graphing calculator, you can actually use that huge list of numbers to see where roots might actually be if the roots are rational. And if it's not making sense, it will make sense in the next video for sure. It looked like if I did a zero test here with the second trace and I choose 0, I'm going to go ahead and see if I can find the value of this root here. I'm going to enter for my left bound as negative 1.5. I'm going to enter for my right bound 0. And my x-intercept does lie in between here, and I'm going to go ahead and find, my guess is negative 1. Let's see if it's a 0, and it is. So what that told me then is when I went back to this page, when I went back to the problem, I tested negative 1 with synthetic division on the polynomial, and I got a 0 for remainder, which means that negative 1 was indeed a 0. I repeated this for 1.2. 1.2 did lie in between the values that I thought the x-intercept was, and when I tested it on my calculator, it came up as a 0. I'm going to ask that you proceed to the next video so we can conclude this problem. Thank you.